Good morning, everybody. It's been a while since we've met in the studio. If you could give some green check marks in chat, and if you had any questions from last day's material, I know I left you guys with some work to do and the simulation, and I said I'd answer any questions you might have had today. So if anything you wanted me to go through, we could. And one other thing is that we were scheduled from 9 till 10:20 or whatever. Turns out I don't have class at KSS, so I might stay a couple minutes late, if that's all right with everyone, just to get through all of the stuff we need to get through today. So there you go. A couple from the assignment, a couple from the learning guide, page 6, number 11, 12. I assume that's off the learning guide there, Taylor. And is there anything else that came up? I'll jump over to the learning guide and then we'll go from there. Page 6, 4, 5, 6. All right. Page 6, number 11 and 12. Of course, I didn't bring my calculator, so you guys are going to have to help me out here. Half-life isotope of sodium is 15 hours. Initial sample contains 1,000 grams sodium 24. What mass of sodium 24 will be left after 3 days and 12 hours? Show your work. All right, we can definitely do that. Ava, what questions did you have out of the learning guide, just so we can make sure we get those as well, and see how we do here. 13 and 14 on page 6. So I'm doing all of the half-life questions. All right, that's okay. All right, so number 11 here says the half-life of sodium is 15 hours. So we need to figure out how many half-lives are going to occur in the amount of time that we're given. That's kind of the first step. Now, sometimes doing these half-life questions, it makes it really easy if you put everything in a table. And it doesn't really matter what your table looks like, but you can start with something like this. So you could have number of half-lives, and then you can have something like time, and then amount. And you can just kind of go through it like this. Just want to make sure I have enough room here. All right, so if I have 0 half-lives, I have 0 time passed, and I have 1,000 grams or a kilogram. And then I just kind of keep going. After 1 half-life, I have 15 hours have passed, and I have 500 grams left. And I just keep plugging away until I end up with the amount that I'm asked to find. So the important thing about the question here is to read it very carefully. It says initial sample contains 1,000 grams sodium 24, and then the question asks for what mass of sodium 24 will be left. You'll notice some questions will ask about the daughter material, so the isotope that's actually created. So it makes the question kind of backwards. So if you've lost 75% of your original isotope, your parent, then you know how much of the daughter has been produced. So you can the questions can vary just depending on what they're asked to do. So I don't know, let's go through this a couple more times and see where we end up. So 2 half-lives is 30 hours, and I'm down to 250 grams. And 3 half-lives is 45 hours, and I'm down to 125 grams. 4 half-lives, not 50, 60 hours. And what am I down? 1262.5 grams. And I can just plug away like that. Now, the question asks for 3 days and 12 hours. So 3 days is 24 plus 24 plus 24, and then another 12. So 24, 48, 60, 72, 84 hours. Did I get that right? 4 is 12, 13, 14, 2, 4, 6, 7, 8. Yeah. So we're looking for 84 hours. Thank you, Ava. So let's see if I can fit another one. 5 is 75 hours. And what are we down to? 31.25. And can I jam one more in here? I can. 60, 80, that gives me 90. And I have 31.25, so 15.5 grams. So if I'm at 84 hours, I'm going to be somewhere between 31 and 15. And you can just go from there. 3 days, 12 hours. Just trying to, generally speaking, when you have these types of questions, there'll always be ones that kind of work out to the exact half-life. So I'm reading this 84 hours and I'm wondering kind of why it's 84. Why isn't it 75 or 90? So generally speaking, this number, the number of hours, will work out to a perfect number of half-lives. Is there a way to work out the exact mass? Yes, there is. And I'm drawing a blank on the equation because there are ones that we use for Physics 11 and we don't use for Science 10. So for this, I think just estimating it'll be fine. I'll see what I can do. I'll find the equation for you guys before the end of class, and we'll see if that works out any better. But essentially using the equation is just going to make your life a lot more difficult than it needs to be. These questions aren't generally this difficult. So there you go. Half-life isotope sulfur 35, it's 87 days, 300 grams. How much will be left after 1 year? You'll need to calculate the number of half-lives, then pass to one decimal place, then use the graph on page 2. So it's asking us to do the same sort of thing and then refer to, of course there is no graph on page 2. You can use one of the charts from up above. Once you figure out the half-life, half-life and percentage charts that we've drawn a few of, you can use one of those to figure it out as well. I'll leave you with that. Let's look at 13 and 14. You can do number 12 the same way with the chart that I showed you. 13, 14. Fossils analyzed, determine percentage of original carbon, 14 remaining is 25. How old is the fossil? So let's do the same chart as we did up above. Half-life, time, and this one we're dealing with percentage. So 0 half-life, 0 time, I have 100%. 1 half-life, 5,730 years. I have 50%, 2 half-lives, 11,460 years, about 25%. So if I wanted to know how old it was, I've gone through 2 half-lives. Each half-life's 5,730 years. And away you go. Does that help you, Ava? 12-gram sample carbon-11 is left in container for 60 minutes. The mass of carbon-11 is now 1.5 grams. What is the half-life of carbon-11? This is just the same sort of process with the table. So you have half-life, time, and in this case, you're starting with a mass in grams. So 0 half-life, 0 time, I started with 12. 1 half-life, I don't know how much time's passed, but I know I'm going to do a half-life, so this is going to be down to 6. 2 half-lives, still don't know time, down to 3. 3 half-lives, still don't know how much time, but I'm down to 1.5. All right, so if I had 3 half-lives occur, and I know that it's in the container for 60 minutes, you could probably figure out a way to go from there. So we know that this is 60 minutes down here. So you have a couple blanks, I guess, to fill in, maybe some thinking to do, and you can kind of work your way backwards to figure out how much time it's going to take to get to 1 half-life. And if you have the time at 1 half-life, you know the half-life of that sample. So that was that. Somebody else had a question about the assignment. Did you want to throw that into chat and I can go and look at it, or maybe we can do it after, or if there's anything else from the learning guide. Just give you guys a second. This is see a couple of you are typing, so I'll just give you a second to get your message in there, and then we'll look at something else, or we will move on to today's material. Half-life of an unknown element, and then 6 and 7 at the end. This is from the assignment, I'm assuming, Ava. Is that right? Okay. I will just jump into here. I still haven't moved that assignment up. I should probably get that done. All right, so this is talking about the simulation that we went through last day, and half-life of an unknown element. Let's see if I can find where that is. About that unknown element. How would you determine the half-life of this unknown element? Write up a little plan here. Estimate the half-life of the element. All right, so if I recall correctly, when you run the simulation, you can look at the half-life. It doesn't necessarily give you an amount of time, but it gives you a little chart where the atoms are decaying. And then it gives you a red line, I believe, where exactly half have decayed. So let's see if I can't run this. All right, so where is the unknown element? It's not the one I want. Uranium, it's not the one I want. I have to Find the right section, I suppose. Carbon-14 measured 5,730 years. How many blah, blah, blah. Okay, so if I add a bunch of this unknown element, I think that's the one there, I have got it. So you can see you can drag this guy around and you can move it to where you want. So if I watch the pie chart in the top corner here, the brown section is the original element and then the green section is the daughter that's produced. So what I want to do is I'm going to play this and then I'm going to just pause it just a little bit before half and then just take a couple steps until I get half. So that's really close to half, 50 and 49. So that turns out to be right there. So that's a way I can find where the half-life or the half point is. So I can just reset it and see if it works a few times. I'll just pause it a little bit right there and then just take a couple steps. And then now it's over here. That was pretty close again. So I'm just keeping an eye on the pie chart when I have 50%. So it's going to be somewhere in here. It's a little bit different each time just because of when the things decide to decay. But you can just go from there and figure out an estimate of where the halfway point of that decay is. So hopefully that helps you out there. And then I believe you asked a couple questions about the last. And then 6 and 7 at the end. So let's go down to the bottom. Make a small sketch of what a decay curve may look like for an unknown element. And you happen upon an antique store. Clerk claims belt that was once worn by Alexander the Great. Your radiocarbon date and find the percentage of carbon to be 75% remaining. Could the belt be genuine? How did you arrive at your answer? So I guess for number 6, all decay curves are going to look the same. They're all that same general sloping where they start really steep, you get half, and then you go from there. So any decay curve we've drawn in the notes or any one you've seen, they all look identical. So if you just sketch something like that, that would be fine. With the unknown element, you had your half-life at about just under 4 seconds or around 4 seconds. So you have 100% of your sample, then you should have 4 seconds pass, then you should have 50% left. Then you should have another 4 seconds pass, you'd be down to 25%, another 4 seconds, and you can just kind of draw it like that. And then this last question, find the percentage of carbon to be 75%. So that means you haven't even gone through one half-life yet. You're about halfway to a half-life. If you had 50% remaining, you would be exactly one half-life. But because you have 75% remaining, you're at about halfway between where you started and a half-life. Now we do know the half-life of carbon-14, and the half-life of carbon-14 is 5,730 years. So if I have 75% of it remaining, that means I'm about halfway through a half-life. That makes sense. So that should be around, what's half of 5,700? About, 2,350 years-ish. So use your judgment to say if it could be genuine or not. How do you sketch it on Word? That's a good question. I guess you could draw a shape, first of all. Can get like a right angle. Yeah, let's do that. I could draw just a line down and then a line over. And then drawing, I guess you can't freehand draw in Word, can you? Is there any like, you can do shapes. What you might be able to do is this what I'm looking for? There you go, that was it. So if you go into the insert and then shapes, there's a squiggly line here, which should let you draw a nice decay curve like that. So there you go, that's how you can draw in Word. Or you could go and just find an image of a decay curve, and then you could just take a screen capture of it using like the snipping tool or something, and then put it into your document. Those would both be good ways to do it. Hopefully that clarifies some of that. Are there any further questions before we mosey on into today's material? I will maybe see if I can find some more decay questions, half-life type questions, because they are a little bit tricky, and maybe give you guys a few more of those for practice, because I think the 4 that are in the learning guide maybe just kind of scratch the surface. All right, I don't see any more questions, so we will move on to today's material. This is one of my favorite sections of Science 10, and I think because I have spent a lot of time studying physics, I enjoy this stuff a lot. And I think it's just really interesting, and students generally find it kind of interesting because you've seen some of this stuff before in your life, and it's kind of exciting stuff. It's kind of scary stuff, but it's kind of exciting stuff. So today we're going to talk about the differences between fission and fusion, and what they are, how we can use them, and sort of what they're used for, I guess. So the important sort of thing here is to draw a distinction between fission and fusion. They kind of sound the same, but they're really different things. And the really easy way to remember it is fusion. You guys know if you fuse something together, or if you go out for dinner and you're eating fusion cuisine, it's taking 2 different types of foods. So you could have like Indian Thai fusion, and they'd a little bit of Thai food, a little Indian food, and kind of mix it together and make it. Fusing something is joining things together. So fusion is a word you're familiar with, joining things together. Fission is probably something you're not as familiar with, and that's breaking something apart. So those are the kind of big ideas. We're going to talk a little bit about power plants, and in Canada, especially on the East Coast, they have nuclear power there, and we don't have any in the West Coast for reasons we'll talk about in a second. But we have something called a CANDU reactor, and this is a picture of one. And CANDU reactors are sort of Canadian technology that's, we set these reactors up all over the world, and they're known as some of the safest nuclear reactors that exist. So we'll take a little bit of a closer look at the inside of a nuclear reactor and see how power is actually generated. So first thing we're going to talk about is fission. So if you have a really heavy nucleus, and you take that heavy nucleus and you split it into 2 or more smaller nuclei, you can end up with a large amount of energy produced. Now, the key here is that if you have something like an oxygen atom, oxygen's relatively stable. It has 8 protons, 8 neutrons. It's kind of small compared to something like uranium, which is 92 protons and 235 for a mass. So a lot of elements aren't radioactive, and they don't want to break apart. They're really stable, they're really happy. But when you get things that are really big, when you get up to like uranium, 92 protons and larger, they become really unstable because there's so many protons in the nucleus, and they're trying to push each other apart. Remember, those positive charges want to repel one another, and they're unstable. So if we add something to them, if we can hit them with something really hard, they'll break apart into two things, and then a bunch of energy will be released. So this is kind of the idea of fission. So nuclear reactions are ones we've already looked at, the alpha, beta, gamma decay type questions you guys did in 7.1. It's the same idea again here. When we have a nuclear equation, the protons and neutrons on either side of the equation, or the arrow, have to add up, so they have to be equal. And we end up changing the actual elements, so the elements get changed from one to the other. When we dealt with chemical equations, when we were balancing and doing things like that, we didn't have to worry about new elements being created. We started with carbon, we ended with carbon. That was the whole basis for balancing chemical equations, was you started with something, then you had to finish with it. But now that we're doing nuclear equations, you can start with uranium and you can end with krypton and barium. It's just kind of like, it doesn't really, make sense if you can start with one element and you end up with something else. But that's what's sort of special about nuclear equations. And we have the most famous physics equation ever, E equals mc squared. Einstein obviously came up with this. And do we know what those letters mean? Does anybody know what E equals mc squared means? And what we can use it to calculate? This is probably the first time in your lives where you're actually able to kind of talk about and understand E equals mc squared in the context of something where it actually makes sense, not just, oh, E equals mc squared is just a fancy physics equation. So what is the E? Alex says energy times mass. That doesn't make sense. You're on the right track though. You've seen it so much. Yeah, it's kind of one of these things that's it's in pop culture. Like everyone knows E equals mc squared. But what does it mean? What is the E? E is energy. I'll give you that one. M. What is the M? What does M usually mean in an equation? You guys have done a little bit of density stuff in grade 8 or 9, I believe. And then C is probably the letter you've never really talked about. Yeah, so E is energy and it's measured in joules. M is mass measured in kilograms. And then C. Does anybody know what C is? C is a constant. It doesn't change. It's actually the speed of light in a vacuum, which is kind of a weird sort of thing to talk about. But light can speed up and slow down depending on what it's traveling through. So we say the speed of light in a vacuum because if you take everything away, and like space is a really good vacuum, it's just how fast light travels. So E equals mc squared. It turns out light travels really fast. And if we take, in these nuclear equations that we're going to deal with, when atoms break apart, or even when they fuse together, we talk about fusion, a little bit of mass gets converted to energy. And some amazing stuff can happen as a result. So, it's 9:30. I wanted to watch this, but then I wasn't going to, but I think I do want to watch it. So I'm going to, if I can find it, we watched A is for Atom, or I asked you guys to watch the first half of A is for Atom. This second part is about 7 minutes long. I might cut it off a little bit early just to save time, but again, this is the 1950s, so this is when we were just figuring out how to do this sort of stuff, and they produced this video. So I'm going to supersize this, see if I can get some sound going, and we'll just watch maybe 5 minutes or so of the second part of A is for Atom, and then we'll talk about some of the ideas that came up in the video, because it does a great job of kind of lining up with what we need to talk about in Science 10.
Mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1,000,000,000,000,000 atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But how to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb. At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission, the graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms, and here's what happens. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which converts the U-238 first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air.
All right. So obviously that was in 1952 or 53 when it was produced, and they didn't really know what the possibilities were for using nuclear energy, so they speculated that they could use it in things like trains and planes. Did it happen? Not in planes yet because of sort of weight restrictions and things like that, but we do have nuclear-powered submarines that some governments have, and some big ships like aircraft carriers and whatnot are nuclear-powered as well. So, you know, they had to speculate, they didn't know, and they thought, hey, maybe we could power whole cities with this stuff, and we do. And it's pretty cool to think that we can do that. So we're going to keep this idea E equals mc squared in the back of our heads for a second, but basically the idea is a little bit of mass gets converted to energy. And like you and me are made of mass, everything around us is made of mass. If we could harness just a small fraction of the energy converting our mass or the mass of some uranium directly into energy, the amount of energy produced is absolutely incredible. And we'll look at that here in a second. So this stuff's really cool and interesting and kind of different. But the only parts that you really get tested on or really come up is these nuclear equations. So just like when you were dealing with the alpha, beta, gamma decay, these nuclear equations are ones that you're going to have to be able to do. So these are an example or two examples of a nuclear equation. You can be given like an image like this one up here. This is a new feature that I have now, got a laser pointer. So the equation is here. And you can see that you have an alpha particle, and it gets smashed into this nitrogen atom. So you're adding these two things together. These are your reactants, and then you have your arrow, and then your products over here. So if you can take an alpha particle, smash it into nitrogen, what can happen is you can produce oxygen, and then you end up with a proton as well. So that's kind of what it looks like in terms of a picture. And then down here you have the same equations, but just in terms of the actual things that are taking part. So alpha particle or helium nucleus, same thing. You have nitrogen, you produce oxygen and a proton. So these are the symbols you don't need to know because they're actually on your formula sheet. But the idea with nuclear equations is that the left side has to equal the right side. And you can end up with all these things like a proton or a hydrogen nucleus. These are the same things. You can have a neutron, which is 1, 0, N, helium nucleus or an alpha particle, an electron or a beta particle. These are all the same things. And they are found on your data booklet. I'm looking for. So this is the very last page of your data booklet. This is page 12. And you can see in the middle here you have all your radioactive symbols. So it doesn't tell you what they are. Alpha particle helium, beta electron, you have a gamma ray, a neutron, a proton, and hydrogen. So these are the things that are going to make up these sort of decay nuclear type equations. They're given to you on the back of your data booklet, so nothing you need to memorize, which is kind of nice. There you go. So here's an example of what these types of questions will look like. The first one's done for us, and then the second one is one we're going to do. So if we start with uranium-235, which is the stuff that likes to undergo fission, and this is kind of the most common decay equation for uranium. You don't need to memorize it, but it is just kind of a common way that uranium will break down. So we take uranium, which is so big, 92 protons in that nucleus. It's really unstable. It's like a huge nucleus. And we take a neutron and we fire it at it. We get that neutron going the right speed, and then it goes into the nucleus of the uranium and it gets absorbed, and the uranium says, oh, I'm too unstable, and it breaks apart into two things. Now the two things it breaks into, they can be different elements, but generally speaking, krypton and barium are kind of the common ones that it'll break down into. You get 3 neutrons which are produced and a bunch of energy. And these 3 neutrons are kind of the important thing that causes the reaction to continue and cause this chain reaction. So that's one way that uranium can break down. The second way, or a second way, not the second way, a second way, is down below. So let's see if you guys can figure out what this missing element is here. So again, we're starting with the same thing. Neutron and uranium-235, they get smashed into one another. We get some cesium produced, we get 3 neutrons, some energy, and what is the missing element? So we're going to kind of do the math here, right? We need to have our protons and neutrons add up on either side. And the tricky part right here is this 3 in front of your neutrons. That means you actually have 3 neutrons here. So you have 3 times whatever is here. Just like when we were balancing chemical equations, we put coefficients in front of things to indicate how many of that thing there were. So in this case, we're indicating that there are 3 neutrons. So what I want you to do is take a second, see if you can do the math, figure out how many neutrons, or how much mass, I should say, goes on the top line here, how many protons go on the bottom line, and then figure out what element we're dealing with for the blank here. So I'll give you a second to do that. I'm going to break out my trusty data booklet, see if I can't figure it out for myself. And if you do get it, throw it in chat, see how we do there. Daily, no idea, I'm confused. Okay, well that's one way. Of course, this is the first time you've ever seen this. It's kind of like the alpha, beta, gamma type questions we were dealing with before, where we had to add up the protons and neutrons on either side of the arrow and figure out what we were dealing with to begin with, what we were dealing with to end with. And you have to end up with the same number on both sides. So, is it rubidium? I don't know, Ava. I haven't gotten that far yet. Ava thinks it's rubidium. Anybody else have an answer? Want to check? See if they agree, disagree with that? Nobody else seems to be piping up. All right, let's go through it together, and we'll see if Ava is right with rubidium. So, we have this equation, and we need to figure out how many protons are on one side of the arrow, and the amount of protons needs to be the same on the other side. And then if we can figure out the mass on one side of the arrow, the mass has to be the same on the other side. So if we look at the bottom numbers to start here, and we have 0 and a 92 on my left. There we go. And over here, we have a 55 as 0. All right, so if I kind of separate everything at my arrow, how many protons do I have on the left side? So I have 0 plus 92, which gives me 92 protons. That's the bottom number, the yellow ones, on the left side of my arrow. On the right side, I have this here. I'm not sure what that is. It's just a blank. And then I have another 55 here. And then I have 0 here. So I have 92 on my reactant side, and I have something plus 55 on my product side. So what is that something? What do I have to add to 55 to get 92? Anybody have their math hat on this morning? Something plus 55 equals 92. Surely we can do this. Surely we can. 37, I don't know. 37 plus 55, let's add it together. 37 plus 55 is 80, 92. What do you know? It's 37. So this little blank down here is going to be 37. And if you recall, the number of protons tells us what element we're dealing with. So if I look on my periodic table and I find element number 37, I can see that that is indeed rubidium. So rubidium has 37 protons. So that's kind of the first half of the question, and well done, Ava, for getting that one. The second is, we need to know the mass of rubidium. We know we have different isotopes of elements. So on the periodic table, if I just take a quick look over, it says rubidium has a mass of 85.5. That is all rubidium in the entire world averaged out. This one atom we're dealing with might be different than that. So let's figure out what it is. So now I'm going to look at the top numbers here, and they're going to have to be equal on either side. So I have one neutron, or 1 and 235. So I have 1 plus 235, which totals 236 on my reactant side. Over here, on my product side, I have a blank. So I'll just draw a little blank here. And then I'm going to add to that 141. And then I'm going to add to that, and this is where it gets a little bit tricky. I have 3 of whatever's here. So that's actually a 3. So 236 is equal to something plus 141 plus 3. So if I just write it up here because I'm running out of room, 236 is equal to something plus 141 plus 3. If I simplify it a little bit further, 236 is equal to something plus 144. What is that something? The missing blank here, which goes in there. 144 plus what equals 236, or 236 minus 144? I mentioned I don't have a calculator in front of me, so to save me some math, one of you could figure out that number for me. It would be greatly appreciated. 92? Anybody agree or disagree with 92? And 144. Let's see, that goes 6, 3. There we go. I like it. So this is 92 up here. So the moral of the story is the missing element, 92, rubidium, and 37. This is the blank we needed. I'm going to supersize it here. So it had a mass of 92, 37 protons, and it was Rb. Now, again, this is where some students get really confused. If you look at a periodic table, I don't think I can rotate this. Might be able to. Maybe, just maybe. Rotate. No dice. All right, let's see if I can find another periodic table. Unit 4, there it is. Here's rubidium on the periodic table. Now, rubidium on the periodic table has a mass of 85.5 and it has an atomic number of 37. This is where students sometimes get really confused because they say, well, Mr. Borden, the 37 was the same, but we have an atomic mass of 92, but on the periodic table, the atomic mass is 85.5. And the reason these can be different, ours is 92 in the example we just did, is because these are different isotopes of the same element. So the mass can change, but if you have something with 37 protons, it has to be rubidium. It can't be anything else. So when you are dealing with nuclear type equations, isotopes, don't get caught up in the mass numbers being different from those on the periodic table because you can deal with isotopes. These are elements that have the same number of protons, but they have different numbers of neutrons. That's why their mass can go up and down. All right, let's continue on with the notes. And we'll look at another example in a second of a fusion type question. So uranium-235 is the unstable isotope, and the key that is important with uranium-235 is when it breaks down, it actually produces 3 new neutrons. And that's what causes the chain reaction. That's the reason we can use uranium-235. Plutonium does the same thing, but plutonium's not a naturally occurring element. So in most fission reactions, weapons like nuclear bombs and explosions, you can take some uranium-235 and you can launch a neutron at it like that. It changes to uranium-236, and then it splits barium and krypton, and you get these 3 other neutrons. Well, it turns out that the 3 neutrons that are produced, like the video we watched, A is for atom, those 3 neutrons can go and hit other atoms and continue the reaction. Remember, if you have a sample of uranium-235, there's going to be billions and billions and billions and billions of atoms in it. Now, if we can control that chain reaction, then we can use it to produce heat or to make a bomb or whatever we might want to do with it. So this is kind of the whole basis of nuclear power and nuclear weapons. So chain reactions is the important part here. The neutrons that are created will go and hit other uranium-235, and it'll make those break down, and that'll go and hit your other uranium-235, and that reaction can get out of control. But if we can control the speed at which it happens, then we can end up producing a bunch of energy or heat, and we can use that heat to do things. And there was a few scientists that were responsible for discovering this, and one of them was Fermi. And Fermi realized the materials could be absorbed, some neutrons could control the chain reaction. There was also this woman, and she is kind of one of these classic examples of how science in the 1900s kind of forgot women. So this is Liz Meitner, and she lived in Germany, I believe, and then during the war, World War II, she fled to Sweden, and she lived the rest of her life there. But she was the one who actually discovered how these atoms could be split and how this chain reaction could be continued. And she was actually studying this with a man named Otto Hahn. And Otto Hahn actually received the Nobel Prize for discovering this sort of chain reaction thing, and she didn't. And it wasn't till only a few years ago, like less than 5 years ago, element 109 on the periodic table was named after her in honor of her actually discovering this stuff. So because women often were forgotten in science, she didn't receive the Nobel Prize, but eventually she got an element named after her on the periodic table. So forevermore, she'll be element 109, which is meitnerium, which happens to be something that's really unstable and only created in laboratories, but still pretty cool. So there you go. So we're going to talk a little bit about CANDU reactors, and basically you just need to know that these things exist, and a little bit of how they work, and kind of some of the reasons why we use nuclear energy and why we wouldn't want to use nuclear energy. But CANDU reactors are really safe. They're recognized around the world for being really efficient, really safe reactors, and they can use fission decay of uranium that doesn't have really high amounts of uranium-235 in it. They have the ability to use really not very pure uranium. So we've sold them to Canada, obviously we have them, South Korea, China, India, Argentina, Romania, Pakistan. They all have CANDU reactors. So what happens is Pakistan says, hey, we need a nuclear reactor, and they contact the Canadian Nuclear Energy Commission, and they say, okay, we'll come over and build one for you. So we go over there, we build it, we train them how to use it, and then they use the reactor to produce energy for their needs, which is pretty cool. The kind of disadvantage to nuclear reactors is the waste that's produced. So we've seen uranium breaks down into krypton and barium, and that krypton and barium are highly radioactive. And the half-lives of these things are many thousands of years. So even after 20 half-lives, the bad stuff that's produced as a byproduct of these reactors, we don't know what to do with it. Now recently in the United States, they've got a big mountain, they've hollowed out the inside of it, and they're just putting all of this nuclear waste in the inside of a mountain because that's kind of how far we've gotten. Some of it gets purified and they pull out the good stuff, and there's still a bunch of stuff that's kicking around that we don't know what to do with, and it will be here and hazardous well beyond humans' lives. So the planet will be empty, I'm sure, one day, and there'll be a bunch of nuclear waste kicking around from when we use this stuff. So that's kind of one of the problems with this. Another problem with nuclear reactors is that they produce some really good stuff, like medical isotopes. So we can use some of the byproducts to diagnose things like cancer, thyroid cancers, medical imaging. We use all these radioactive byproducts. But another byproduct that's produced is plutonium. And if the wrong people get the plutonium, they can make nuclear bombs out of it, which is a bit of a problem. There's actually an interesting story about, I guess almost 10 years ago now, Iran, a country in the Middle East, was saying, oh yes, we're just pursuing a nuclear power in our country, and there's a few countries that didn't believe them, like the United States and Israel. And what happened is, when you want to purify uranium, you put it in a centrifuge. So you take uranium and you spin it really fast, and that separates the uranium-235 and the uranium-238 from one another. The uranium-235 is the good stuff for nuclear bombs, and the bad stuff is uranium-238. It doesn't fission like uranium-235 does. So what actually happened was no one ever admitted to it, but everyone knows it was the United States and Israel together. They created a computer virus, and it was called the Stuxnet virus, and it infected computers all over the world. Like, just yours and my computers were infected by this virus, and it didn't do anything. And people were really confused as to why this virus was everywhere, not doing anything on all these computers. And it turns out that this virus infected the computers at the Iranian nuclear facility, where they had these centrifuges that were enriching uranium. And basically, once the virus entered the Iranian computers, it knew where it was, and it said, okay, this is kind of where I'm supposed to be now that I've infected millions and millions of computers. These are the computers we want to infect. And it basically turned on all of their centrifuges and just spun them uncontrollably until they just disintegrated. So basically, a computer virus that we think the Americans and the Israelis made infected the Iranian nuclear centrifuges and set their nuclear program back probably about 10 to 15 years, which is probably, I don't know, I'm not a political analyst, but it might be a good thing. So this is the inside of a CANDU reactor. Right here you have your reactor core, and this is a big containment dome made of concrete. So this is a couple feet of concrete. And in the reactor core, you have these little machines that put in new rods. So they put uranium in here. And in this red loop, we have water. It's generally heavy water, which is a special type of water. But the water circulates and it gets really hot, and it goes into a second loop, which also has water in it. And the steam gets created, spins a turbine, which spins a generator, which collects electricity, and then it gets condensed, and then it goes back in, and this second loop gets cycled. The third loop is always connected to some external water source. So you'll see that nuclear generating stations are always built on either a lake or a river. They need lots of fresh water to cool the core. Sometimes they can be built on oceans, but they have to desalinate the water generally. So the CANDU reactors are really safe because they have 3 closed loops. So the radiation that's all in the middle in the reactor core, it's contained in here. If something bad were to happen, it's all contained within this loop. So all of the radiation's contained in here. And then you have the second loop with just water in it, which is slightly radioactive, but not really. And then this third loop is just water from the outside, and it's not radioactive at all. So 3 different loops, very safe. No radiation leaves this reactor core center, and it's a great way to do things. There's other reactors that have 2 loops that are less safe, and all sorts of other stuff like that. So this is the idea behind this sort of chain reaction. You have a moderator, which is heavy water, which is kind of like H3O almost, instead of H2O. It slows down the neutrons. Neutrons can get going so fast that they don't get absorbed by uranium and they just zip right through them. That breaks down, 3 neutrons are produced, 3 more uranium split, 3 neutrons are produced here, 3 neutrons are produced here, 3 neutrons are produced here. It just keeps going. This is the chain reaction. Control rods are generally made of graphite, like the stuff in your pencil, and they actually absorb neutrons. So if you want to slow down a nuclear reaction, you put in the control rods down from the top, they absorb a bunch of neutrons that are flying around, the reaction slows down or stops. If you want to speed up reaction, you raise it up the control rods, the uranium breaks down faster, the more neutrons split, and that's how you can control a nuclear reactor. There have been 4 technically, but 3 major nuclear meltdowns in all of nuclear energy. So 3 Mile Island's in New York State, Chernobyl is in the Ukraine, and Fukushima is in Japan. So this behind me here, this big picture, this is Chernobyl in Ukraine, and the reactor melted down there. And they've created this large dome, and they're actually going to put it on tracks, and they're going to slide this dome right over the reactor because it's so radioactive there that nobody can really get close to the reactor. And if you can imagine, this is one of those cranes they build skyscrapers with. That's how big this dome is. These are cars down here, these little dots. You can see the little dots here. So that's a car. That's how big this dome is. So it's actually one of the biggest structures we've ever built. It's a couple $2 billion worth of construction. They're going to slide it over this to contain the radiation. They're going to start to dismantle the reactor that melted down. This is Fukushima. 3 of the reactors actually exploded during the tsunami. And what they're going to do here is, what's happening is all of the rain that falls on here is going down. It kind of goes through the reactors, and then it enters the ground. And the water from the ground is flowing out, and this is the ocean right here. So what they've decided to do is, they have a refrigerator plant, and they've drilled holes down into the ground all the way around the Fukushima reactor, or reactors, and they're going to freeze the ground and create an ice wall underground so that groundwater can't enter and then exit here. That's kind of how they plan on containing the radiation or the radioactive materials there from going right into the ocean. So kind of crazy, but that's how they're doing it. So that's fission. Does anybody have any questions on fission? Negative. All right. So fission, taking something big, generally uranium or plutonium, breaking it down into smaller things. A little bit of mass gets converted to energy, and you end up with energy being created. Nuclear fusion is something that takes 2 really small things like hydrogen or helium. It combines them together, a bunch of energy is produced, and the great thing about fusion is that the nuclear byproducts aren't radioactive. So this stuff here, if you can imagine getting a couple hydrogens, so these red guys are just protons. So you smash 2 hydrogens together, it creates this isotope of hydrogen. You get that and smash those together, and you end up eventually at the end of your reaction producing helium. So fusion takes hydrogen, which is the most abundant element, or abundant element in the universe, and it makes helium out of it. And you can fuse helium to make bigger things, but this is kind of the idea of how fusion works. So the really cool thing about fusion is that there's nothing bad produced. We get massive amounts of energy out of it, but no bad byproducts. We don't have radioactive materials with half-lives of thousands of years. So where does fusion happen? It happens in the core of the sun. The sun is one big fusion reaction. And we have started to harness fusion power, but we're not very good at it. Basically, the amount of temperature and pressure that needs to be created to fuse even the smallest elements like hydrogen and helium together is it takes more energy to get these things to fuse than we're actually getting out of the reactions right now. We're getting close to being able to harness fusion power, but we're not kind of there yet. So that's kind of the goal, is to get cold fusion. And cold fusion is fusion that can happen at a temperature and a pressure that will allow us to get energy out. So at the bottom here, this is what a fusion reaction looks like. This is an isotope of hydrogen. This is deuterium and tritium. If we can get these two isotopes to stick, we produce helium, a neutron, and a bunch of energy. So that's kind of where we're at with fusion. We haven't harnessed it yet, but we're getting close. So let's do an example. We did a fission example for a warm-up. Now you guys can do this fusion one, and we'll see how you do. So if I can take deuterium and tritium, stick them together, I end up with helium, a neutron, and a bunch of energy. The 2 plus 3 is 5, 4 plus 1 is 5, 1 plus 1 is 2, equals 2 plus 0 is 2. Figure out what the missing element is here. Add up your masses on the reactant side, has to equal your masses on the product side. Add up your protons on the reactant side, has to equal your protons on the product side. What is the element? What is its mass? I'll give you a second. You guys should be able to get this one really quick. Math is very small and easy. Probably do it in your head. What is there? What is that blank? Hydrogen, okay. Hydrogen's a good start, but is it hydrogen with 1 proton, 0 neutrons, or is it an isotope of hydrogen? I'm not looking for the actual name, but just the mass. Is it a kind of the standard hydrogen that just has a mass of 1, or is it hydrogen that has a mass of maybe something else? I'm going to take a little screen grab of it here, and we'll take it over. See if we can do it. Mass of 3, Abby says. Abby just showed up and she's throwing out answers already. I like it. All right, so we kind of separated at the arrow. It's kind of like an equal sign in a math equation. I have 6 plus 1, which is going to equal 7. Over here I have something plus 4, and it has to equal 7. So that's going to be a 3. So you can put a 3 there. And then on the bottom, I have 3 plus 0, which is 3. And over here I have something plus 2. So a 1 will give me 3. So this is a 1 and a 3. I look for element number 1 on the periodic table. I see that it's hydrogen. And this isn't hydrogen with a mass of 1 like it normally has. This is hydrogen with a mass of 3, which is an isotope of hydrogen, which is called tritium. You don't need to know that, but now you do. So yeah, there you go. That's a really easy example. And sometimes when you get to some of these fission examples, it's really good idea to go back and look at maybe some of the fusion ones with the numbers that are really small, easy to deal with, and you can kind of jog your memory and be like, oh yeah, that's how I came up with that. So yeah, you guys are right. You're on the right track there. And that's kind of it for fission and fusion. If you can do these equations, that's kind of the meat and potatoes of this unit. And those are the types of examples you'll see. You also end up answering questions about nuclear reactors, about why I've seen questions like, why is nuclear reactors, why don't all countries have nuclear reactors? Why did Japan shut down all of their nuclear reactors after the Fukushima disaster? Why are countries moving away from nuclear power? Why are some countries moving towards nuclear power? So just being able to understand what's good about nuclear energy, like massive amounts of energy can be produced with very little reactants. It's carbon neutral, so when we break down uranium, we're not producing any carbon. And we have a really big problem now with energy burning fossil fuels. and creating things like carbon dioxide. So there's absolutely no carbon involved when we produce energy with nuclear power plants. So what are some of the bad things about nuclear power plants? Why would we not want to generate power using nuclear power plants? Taylor, no, we don't end up ever talking about human anatomy in Science 10. I think you have to wait till biology 12 even for human anatomy. Nuclear power, what's bad about it? Why? Like, it's great in terms of the amount of energy that's produced, very little material in order to produce that much energy. What's bad about it? Why don't some countries like nuclear power? I can think of maybe like 3 reasons off the top of my head. Any ideas? No ideas. Well, apparently I didn't do a very good job of talking about any of this stuff today. I failed as a teacher. Nuclear energy. It's hard to control. I wouldn't say, well, I guess we have very good engineers that can control this stuff. It's maybe a safety concern, right? You don't want this nuclear stuff getting into the wrong hands. If bad people in the world end up with some uranium, they could make a bomb out of it, or plutonium, which are byproducts. So the byproducts of nuclear reactors are bad. Either can be made into weapons, or they can be radioactive for thousands, if not millions of years. So the byproducts are really bad. Safety is a concern. When a hydroelectric dam, kind of one of the generators breaks down, it's no big deal. But when a nuclear power plant breaks down, really bad things can happen. You can get meltdowns. Thousands of people died as a result of the Chernobyl nuclear meltdown. So those are some of the reasons why nuclear power isn't kind of more widely used. There's a lot of safety issues with it. Well, I mean, money is important to talk about, but generally speaking, nations need energy. We need lights. We need things to power our houses and cars and everything else. So, a government will generally spend millions and millions of dollars developing some way to generate electricity, and then they'll charge people for it and slowly get the money back. So yeah, money is a concern, but it's actually a little bit cheaper than burning gas and stuff like that. We have about 10 minutes left. Yep, 10 minutes left. And this is not really part of the curriculum. I mean, it has to do with nuclear energy. But it's kind of like a history lesson. And there's a couple reasons I like to share some of this stuff, and kind of connects a lot of things that you guys are kind of aware of and not aware of. You're so far removed from World War II, but I think it's important to talk about. So I'm just going to kind of blather on here for about 10 minutes, and then we'll call it a day. I will get some more decay type questions for you guys for next day. And this is actually it for Unit 7. That's kind of all there is to it. So we'll actually jump into Unit 8 on Thursday's class. And I'll kind of wrap it up and answer any questions you guys might have in terms of Unit 7. So when's Unit 7 due? Let's make Unit 7 due on Monday. Unit 8 is up and ready to print. Yeah, Taylor, it's there. And I just want to talk about this real quick, and then I'll set you guys free for the day. So this was in 1939, and this is a letter. I'm not going to read the whole thing for you guys, but it's a really interesting letter. It's written from Albert Einstein. You guys are all familiar with Albert Einstein. And it was written to Roosevelt, who was the President of the United States. So at this point, it was kind of the World War II was happening. Einstein had fled Germany and moved to New York State, and he was just living there, being Einstein and smart and things. And he basically sent this letter to Roosevelt saying that, hey, there's some scientists. We talked about Fermi, Enrico Fermi and Leo Szilard were the two scientists. that were working on sort of this theory that they could take uranium and they could break it down. And they had done studies, and because of people like Hans Otto and Liz Meitner, had said, hey, this uranium is producing neutrons when it's breaking down, and these neutrons can hit other things and break those down, and it just creates this chain reaction. So Einstein said, hey, these two scientists have started studying this nuclear sort of decay. We're really worried that it can be made into a weapon. And at this time, Germany had stopped exporting uranium out of Europe. And basically, Einstein was saying they could probably make a bomb with this stuff. And he was telling Roosevelt to do something about it, else the Germans would come up with this weapon first, and it would change the face of war. So this is 1939. We hadn't started nuclear power plants. There was no bombs yet. Nothing crazy. People were fighting a war, but it was just kind of the environment at the time. And so basically, Germany had controlled parts of Czechoslovakia where there was uranium mines, and they stopped selling it into the public, not to the public, but to like other nations and things like that. So Einstein said, hey, uranium can do this crazy stuff, and the Germans have stopped selling uranium. So there's something going on here, and you guys need to deal with it. So what Theodore FDR, or Roosevelt, he started a program called the Manhattan Project. And the Manhattan Project was a secret project in order to create the first nuclear weapon. Now, there's some really interesting sort of connections. The A is for atom talked about Oak Ridge, where the Manhattan Project took place. This is kind of where it was started out of. And basically, all of these dots all over the country, United States, they all worked independently of one another. Nobody really knew what was going on, but they were given a task, and the people in these big plants were doing these things, and they said, go do this, build this, and they didn't know why, and then all of these things were kind of happening all over the United States. You'll notice that there's two places in Canada, and one's actually really close to us, and Trail, BC. Has anybody been to Trail, BC? Is on the map here. Anyone ever been to Trail? Nobody's been to Trail before? You drive like east, and it's a small little community on the Columbia River. That's amazing. Nobody, there's like, anyways. Yeah, Shayna's been to Trail. What did you think of Trail, Shayna? The reason I talk about Trail is it was part of this whole Manhattan Project, but my family, not me, but my grandparents and my dad, they grew up and lived in Trail. And Trail's a tiny little town, and it has a big, it's called Teck-Cominco, and basically what they do is take rocks from all over Canada, and they refine the rocks down into ores, produce things like nickel and all sorts of stuff. You grew up in 100 Mile House. So Trail has a big smelter plant where metals were produced. Now, my grandfather actually worked for Teck-Cominco. It was called Teck at the time, or Cominco. Now it's Teck-Cominco. He worked there, and he was actually part of the Manhattan Project. He worked in secrecy in a part of the plant where no one really knew what was going on. And what they were actually doing in Trail was making something called heavy water, which is using an isotope of hydrogen. It's called deuterium, and they make water. And basically this heavy water is used in nuclear power plants as a moderator. It slows down the neutrons so the reaction can take place. So my grandfather actually got a certificate of recognition from the United States government for being part of the Manhattan Project. So that's why I think it's really cool. That's why I love this stuff. But what happened was in Trail, they made heavy water, and Trail is on the Columbia River, which kind of flows down into Richland or Hanford, Washington, where they had a nuclear reactor going there in Hanford. And in Hanford, they were refining uranium, which was actually mined in northern Canada. up in the kind of Canadian Shield here was all the uranium that was used in the first nuclear weapons. In Richmond, they were making uranium-235. They were enriching it. In Oak Ridge, they're making plutonium. Down here in New Mexico is where the first nuclear bomb was ever detonated. And yeah, so basically this was happening all over the United States. All of these things were happening. So this is a picture of the Techcominco plant in Trail. It's up on the hill next to the Columbia River. And all of the water that leaves Okanagan Lake flows into the Columbia River down through here. And this was the bridge that goes over the Columbia, separating the plant, and then Trails Town is on the other side of the bridge. So that is Techcominco, where heavy water was made, which developed the first nuclear weapons, which ended World War II. Pretty crazy stuff. I think it's always interesting to watch some footage of nuclear weapons being detonated because it's kind of scary and humbling at the same time. So I like to do that. Do you know how artificial reactions differ from natural radioactive decay? Interesting that there's a place in Africa where the concentration of uranium was so high that it naturally started to melt down right in the ground. So this happens in nature, Ava. There's actually a place in Africa where it's kind of the only natural known sort of chain reaction to happen outside of human control. Now, in a nuclear power plant, we can control the chain reaction. We make a reaction happen really slowly, and we can use the heat and stuff for that. If the reaction happens really fast, then we create a bomb. So there's really not a lot of difference between a nuclear bomb and a power plant, other than kind of the geometry of the reactor core is made in a way such that it won't turn into a bomb. But they melt down and bad things happen. So let's watch a couple of little videos here, and then we'll shut her down for the day. This is kind of a really dramatic music. So these people are witnessing nuclear bombs going off. So these are all fission bombs, and fission bombs create a bunch of energy really quickly. And you'll notice in all of the footage, some things happen. So you can see on like these transformers, the stuff looks like it's coming off of all these structures. And basically, what's happening is when a nuclear bomb goes off, it creates so much light and so much radiation that things like paint lights on fire. All these structures will ignite on fire because of the light that's created. So kind of think of it this way. If you're lying in your bedroom at night, your eyes are closed, and somebody sneaks into your bedroom and they turn on the lights. Even though your eyes are closed, you can still see a little bit of light through your eyelids. Now, if you were looking at a nuclear bomb when it detonated and you were close enough, a nuclear bomb produces so much light and so much radiation that even if your eyes were closed, you would go blind. That's how bright it is. So when you see nuclear bombs happen, or these detonations occur, all of the stuff kind of lights on fire because of so much energy is produced, and then the shock wave of the actual explosion hits and knocks things down. So it's kind of a two-step sort of destructive process. The first step is the radiation that's released lights everything on fire, and then the shock wave comes through and it puts out the fire and knocks everything down. And the actual amazing part of this is going back to Einstein's E = mc squared equation. The actual amount of matter that's converted to energy in these explosions, the actual amount of matter that's converted directly to energy is less than a gram. So E = mc squared is this kind of sort of really meaningful equation that doesn't really look that amazing at first, but the amount of energy that's produced, literally, if you took a penny and you cut it into 3 parts, if you could convert 2 of those parts of a penny into pure energy, that's what's going on when these bombs are exploding. That much mass is getting converted to energy, causing this much destruction. So that's why nuclear weapons are so amazing and dangerous. This is the largest bomb ever detonated. It's a 100 megaton bomb. It was detonated by, a 50 megaton bomb. It was detonated by the Soviets And it's 50 megatons, which is 50 million tons of TNT. That's the equivalent. This isn't actually the bomb. That's one being detonated underwater. But here's the this 50 megaton bomb. The pilot that dropped the bomb barely survived. So you can see the mushroom cloud, and it doesn't really look that big or that scary, but that's kind of the crater that was created. But when we start talking about how big it was, there is the explosion from a long ways away. It's really nothing to really look at, but if we look at some of the facts associated with it, things like this. It was called the SAR bomb. SAR bomb was a fusion bomb, and the only way we can get atoms to fuse together is if we can get temperatures high enough and pressures high enough. And in order to make a hydrogen bomb or a fusion bomb go off, you start it with a fission bomb. That's the only way we can really effectively create temperature and pressure sufficient on Earth to make atoms fuse together, is by igniting a fission bomb first, which causes the hydrogen to fuse, which makes an even bigger explosion. So here we go. October 30th, 1961. It was originally designed to be a 100 megaton, but it actually detonated. They cut it in half to about 50 to 58 megatons. So that's million tons of TNT. That's what a megaton is. Here we go. It was blah, 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 is equivalent to that many times. So the bombs that were dropped on Hiroshima and Nagasaki in Japan that ended the war, this bomb was 1,500 times bigger. Star bomb, I always forget all this stuff. The guy had, 45 kilometers away when he was in the bomb. Fireball and mushroom cloud, this is pretty incredible. The altitude of the Reese Plain was visible for almost 1,000 kilometers. The mushroom cloud extended 64 kilometers into the atmosphere. The atmosphere is only about 100 kilometers thick, so that's incredible. Over 7 times the height of Mount Everest. It went into the stratosphere, well into the mesosphere. Clouds don't go that high. It was 95 kilometers away. Basically, the heat from the explosion could cause third-degree burns. So a sunburn is a second-degree burn. A third-degree burn basically kills your skin. If you were 100 kilometers away, so 100 kilometers away from this bomb, if you were standing there, you'd get third-degree burns. So that means your skin would basically be destroyed, all 3 layers of skin. Shockwave absorbed in the air, and you could literally see the shockwave 700 kilometers away. And window panes were broken at distances of 1,000 kilometers away, even in parts of Norway and Finland. 1,000 kilometers. Think of something that's 1,000 kilometers away from Kelowna. So we're talking maybe in Saskatchewan. Is that 1,000 kilometers away, Mr. Ross? Yeah, about 1,000 K to Saskatchewan. So if this bomb went off in Winnipeg, or not that far, Saskatoon, you would be able to see the light. It would look like the sun was rising again if you were looking to the east. So that's how bright this thing was. In Saskatoon. Incredible. The energy actually measured an 8.1 on the Richter scale. The shockwave went around Earth 3 times, and it could still be measured on its 3rd trip around the world. So the shockwave went around Earth once, twice, and on the 3rd time it could still be measured on seismic recordings. It's just like, it's absolutely incredible to think that humans can produce something on this sort of scale and magnitude. It's scary, and yeah. How did I not know about this? You guys grew up in a time where you're lucky to be in sort of a non-nuclear sort of world where people don't take for granted these sorts of things, and they exist. I'm not going to watch this because it's about 10 minutes long and I've kept you guys a few minutes late already, but maybe we'll watch it at the beginning of next class. if you want to watch it online. It's really cool time-lapse map of every nuclear bomb ever detonated on Earth from 1945 when the first one was dropped in New Mexico, and then to 1998. And after 98, very few nuclear bombs have actually been detonated. Nations around the world have decided to not detonate them above ground because the radiation that gets released into the atmosphere is not good. And now the United States and many countries have computers that are strong enough to actually simulate what a nuclear explosion would do if they alter things. So basically, computers are powerful enough now to simulate nuclear explosions where we don't actually have to detonate these things. But we talked about North Korea, who doesn't have these big, super powerful computers, and they actually have recently detonated a few nuclear weapons just to test it out. Yes, Ava, for sure. So next class, we'll talk a little bit more about this. I'll find some more decay equations, half-life sort of stuff, and we'll spend some time reviewing for the test. There's also the module, I think it's module 2 exam, which is all the chemistry stuff together with this radiation stuff that's coming up as well. So we'll spend some time reviewing next day for sure. I think we don't need to get into chapter 8 next day, but if we run out of stuff to talk about, maybe we will. But let's plan on doing some review next class, and then we'll start chapter 8 the following week. And I'll have some more decay type equations for you guys, half-life stuff. I'll try to find some more nuclear equations because I know there's not a bunch in the learning guide. And then we'll talk a little bit about the module exam, and we'll leave it there. Hopefully that's all right. Thanks for staying a little bit late with me today, and we will start next day with some review. Does anybody have any questions before we go? Negative. All right, great. Have a great afternoon, guys, and we'll talk to you on Thursday.